Alright, so this is the AP Chemistry lesson video for Chapter 10. It's Part 1, and I'm going to cover 10.1 through 10.3. Before I start, I would like to give a special shout out to Sarah from the Kingdom of Bahrain. Thank you for watching my videos, so I hope you take the time to watch this one and hear my shout out to you. So thank you for your kind words. Alright, so let's go ahead and get started. So we're in Chapter 10, which is on gas laws, which is one of my favorites. Of course, we all know they're all my favorites. So let's start with 10.1, characteristics of gases. So air is a complex mixture of several substances, primarily nitrogen, about 78% of our atmosphere, and oxygen is only about 21%. A lot of people, they assume because we breathe oxygen, that is the primary makeup of air, but it's actually nitrogen. And then there's small amounts of several other gases. So the most compounds that exist as gases are molecular. They have low molar masses and they are made of only nonmetals. But you should of course know that because once we say it's molecular, molecular tend to be made of nonmetals. So for example, CO, carbon monoxide, CO2, carbon dioxide, CH4, methane, NO2, nitrogen dioxide, and SO2, sulfur dioxide. So notice that they are all nonmetals. A vapor is a substance in the gaseous state that exists as a liquid or solid under ordinary conditions. So for example, the oxygen we breathe, which is O2 by the way, because it's a diatomic, that is naturally a gas at room temperature, so we call it oxygen gas. But water is normally a liquid at room temperature. We have to heat it up to its boiling point to become a gas, so we call it water vapor. Okay, so vapor just means we had to heat it to make it turn into a gas. So a gas expands to fill its container, so the volume of a gas always equals the volume of the container. So whereas a liquid, we can fill a beaker part way with a liquid, and even though the beaker might hold 500 milliliters, we might only have 100 milliliters of water. For a gas, it will always expand to fill. Gases are highly compressible because the particles are far apart, so we can squeeze them closer together. Gases form homogeneous mixtures with each other regardless of the identities or relative proportions of the component gases. So if I put two gases together, they are going to mix together homogeneously. And gas particles are far apart and act independently of one another. So if you remember from honors chemistry, we said that gas particles, we assume they have no intermolecular forces. That's because they're moving so fast and they're far apart. Now, of course, in reality, they do have small intermolecular forces. But for the most part, we can kind of ignore those. So, section 1 was pretty easy. So section 10.2, we're going to focus on pressure. So pressure is a force that acts on a given area. So pressure is just force over area. So pressure's units are Pascal, PA, that's our SI unit of pressure. Force will be in newtons, and area will be in meters squared. The SI unit for pressure, like I just said, is the Pascal, which is PA. However, if you had anything for honors, you know that most of the time, though, we focus on kPa. Okay, the actual SI unit is PA, and it's a Newton per meter squared, and that just comes from this formula right here, because you have newtons on top, meters squared on bottom. Other units of pressure that we will use more commonly are atmospheres, millimeters of mercury, torr, and kilopascals. And so this is a conversion to get between those. So 1 atmosphere equals 760 millimeters of mercury equals 760 torr equals 101.3 kilopascals. So you got to be careful. Pascal is SI, but kilopascals is what we will more commonly use. So how do we measure pressure? Well, we use a barometer. So a barometer is a device used to measure atmospheric pressure. Standard atmospheric pressure is the pressure at sea level and can support a column of mercury 760 millimeters high. So that's where this 760 millimeters of mercury comes from. Because a barometer, it's like a long, thin test tube. So one end's open, the other end's closed. They fill it all the way with mercury to the very top. And of course, they wouldn't do this with their hands because mercury is poisonous. But then they cover the top, flip it over into a pool of mercury. And so if you notice, the mercury doesn't stay at the very top because some of it is going to come out. And so what you're left with at the top is a vacuum. There's no air up here, there's just nothing. So what's holding the rest of the mercury in is atmospheric pressure because it's pressing down on the pool of mercury, which keeps the column of mercury up high. And so if you're at sea level or 1 atm, it will be 760 millimeters high. If we increase pressure, it will make the height go higher, so it would read a higher pressure. If we decrease pressure, then the column would go lower and we would see lower than 760. So that's how a barometer works. So let's look at some converting of pressure. So it says convert 0.357 atm to torr. Okay, so y'all, we follow the golden rule every time. We have 0.357 ATM. And so, of course, I follow the golden rule. Whatever unit I have on top goes on bottom. And so, y'all, remember, this is our conversion factor. 1 ATM equals 760 millimeters of mercury equals 760 torr equals 101.3 kPa. So I say, well, how many ATM? Well, it's 1 ATM right there. Okay? And then we're going to torr. So I can click that. How many torr? I put 760 on top. Okay, so y'all, when you use this big conversion factor, you don't have to kind of work your way across the conversion factor. You just pull out whatever two parts you need. It doesn't matter. Okay? And so then, since both numbers are on top, I'm going to multiply. And for this one, I got 271.32. And then my ATMs cancel, so I'm left with torr, so my answer would be torr. Okay? So again, hopefully you remember this from honors, because we've done this before. Alright, so next we have torr to ATM. So I start with my 6.6 times 10 to the negative 2 torr. So of course golden rule says I have to put torr on bottom. So in that big conversion factor I showed you, it said 760 torr. And we're trying to get to ATM. Well, it said equals 1 ATM. So my torr cancels. Since one number is on top and one's on bottom, I'm going to divide. And for this one, I got 8.68 times 10 to the negative 5, and my unit, of course, would be ATM. Okay, so hopefully these aren't very tricky. These aren't meant to be very tricky. All right, and our last one, it says convert kilopascals to torr. So I start with my 147.2 kPa, and then I put kPa on bottom, of course, because I'm following the golden rule. So how many kPa? Well, my conversion factor said 101.3. And then that equals 760 torr. And remember, y'all, I'm just pulling these numbers from that big conversion factor. The 1 ATM equals 760 millimeters of mercury equals 760 torr equals 101.3 kPa. All right, so my kPa cancels, so I'm going to multiply my top numbers and divide by my bottom number. And so for this one, I ended up getting 1004.36, and then my unit, of course, is torr. Just like that. Alright, so again, hopefully you remember this from honors and you're like, oh good, I already know this and we can move on. A lot of this chapter we learned in honors. There will be a few little surprises in there though. You know, we're on block scheduling. I can only get through as much as I can. Alright, so y'all pause the video, try these on your own, and then we'll look at them together. So I'll assume you've already done that. Alright, so it says in countries that use the metric system, which those countries are much smarter than we are, atmospheric pressure in weather reports is given in kilopascals. Convert a pressure of 745 torr to kilopascals. Okay, so we're just going from torr to kilopascals. So we have 745 torr. And so, of course, golden rule says torr has to go on bottom. And so how many? Well, from our conversion factor is 760. And we're trying to get to kPa. So on our conversion factor is 101.3 kPa. So my torr cancel. So I multiply the top, divide the bottom, and for this one I got 99.3 kPa. Just like that. Alright, so hopefully y'all got that one right. So the bottom one's a little different, but remember y'all, I've shown you how to convert. So you should be able to convert using any conversion factor they give you. You just follow the golden rule every time. So it says an English unit of pressure used in engineering is pounds per square inch, or PSI. So it says 1 ATM equals 14.7 pounds per square inch. If a pressure is reported as 91.5 PSI, express the measurement in ATM. So y'all, it doesn't matter that you might never have seen this conversion factor before. You know how to follow the golden rule. So we start with what we know. We have 91.5 PSI, or you could write pounds per inch squared. It doesn't matter. So I have to put PSI on bottom, or pounds per square inch on bottom. So I put my 14.7 on bottom. And then that equals 1 ATM. And that's it. So see y'all, once you know to follow the golden rule, you should be able to convert literally anything ever that you're given. So I ended up getting 6.22 ATM. So hopefully you got that one right. So like when you're taking the AP exam, then don't get stressed out if you see a conversion you might not have never seen before. You can still do it, you just follow the golden rule. Alright, so hopefully y'all got this right. So let's move on to a manometer. So a manometer is a device that we use in the lab to measure pressure. So it's kind of like this. Ooh, this picture isn't super clear, but that's okay. It's probably not clear in the video anyway. But in reality, it's not very clear. So you can have a container that holds a gas, and it has this kind of S-shaped tube. Sometimes the tube is open, sometimes the tube is closed. And then there is a column of mercury in there. Now, if the pressure inside the flask is the same as the pressure outside the flask, the two sides of the mercury will be at equal levels. But if you build up pressure inside the flask, that gas will try to escape, so it'll push down on this side of the mercury and the other side will go up. So the difference in these two, that's what we call the height. Okay? So pressure is based on the difference in the height of the two arms. So we say pressure of the gas equals pressure of the atmosphere, that will be the pressure out here, plus the height of the mercury. Okay, so you have to keep in mind, y'all, this is going to be in millimeters of mercury most likely, because they're going to give you the millimeters height of both sides of the arm of the mercury columns. So you may have to do some converting depending on what unit they ask you for. Alright, so let's look at the first one together. It says a sample of gas is placed in a flask attached to a manometer, and the level of the mercury in the open end arm has a height of 136.4. So that we can see a visual of this, I'm just going to label it on here. So we have 136.4 millimeters. So see, that's the open end, because you might not be able to tell, but it's open. Oh, well, it tells you right here it's open if you can't see it. All right, and this should say arm. My gosh, me and my typos. And the arm that is in contact with the gas has a height of 103.8 millimeters. So that means this right here is 103.8 millimeters. Okay, so I have this height, I have this height. What is the pressure of the gas in ATM if the atmospheric pressure was 764.7 torr? Okay, so here's where it gets a little weird. We want pressure in ATM, but they gave me torr right here, but yet I'm working with, I'm working with millimeters of mercury here. Okay, so first thing we need to do is find that height. Okay, so for the height, for this right here, I just subtract the two sides. So I'm going to do 136.4 millimeters minus 103.8 millimeters. Okay, and so once I do that, I ended up getting 32.6 millimeters of mercury. All right, so then we know, oh, whoops, here, let me go back to, now that we've seen the picture, let me go back to my other slide. So, oh, okay, y'all can still read that. It's good enough. It's good enough. All right, and so we know our formula is P of our gas equals pressure of the atmosphere plus that height. Okay, that's what the H stands for. Okay, so we have the height, 32.6 millimeters of mercury. If you remember from your conversion factor, 760 millimeters of mercury equals 760 torr. So I can just change this from torr to millimeters of mercury. It's the same thing. Okay, so my atmosphere pressure was 764.7 millimeters of mercury plus my pressure from the height, which is 32.6 millimeters of mercury. And so once I add those two together, I got, where am I looking? Okay, I see it, 797.3 torr. Oh, sorry, I would get millimeters of mercury. On my paper, I must have kept it in torr. It doesn't matter which one you use, that neither of them are what the question asks us for. Okay, but it says what is the pressure of gas in ATM. Okay, so now I would need to switch it to ATM. So you got to be careful, y'all. Always make sure you're going to the unit they ask for. So I put my 760 millimeters of mercury on bottom. So see, these are the conversions we just learned. That equals 1 ATM. So I just divide my two numbers, and I got 1.05 ATM. Okay, so all we did, y'all, was subtract the two sides of the mercury to get the pressure H, our pH, and we did our atmosphere plus the pH to get our final pressure. Now this would be the answer, except it says what is the pressure of the gas in ATM. So I had to convert to ATM. All right, so y'all try the next one real quick. As always, just pause the video. You can try it on your own, and I'll assume you've done that, and we'll look at it together. It's just a simple conversion. You are going to two things though, PA and KPA. All right, so it says converted pressure of 0.975 ATM to PA and KPA. I'm going to go to KPA first because that's in our conversion factor. So I know ATM has to go on bottom and it's 1, that just comes from that conversion factor a few slides ago, and I know that equals 101.3 kPa. So my ATM canceled, so I multiply, and for this, I got 106.37 kPa. But it also asked me to go to pascals. So y'all, kilo always means 1,000. So 1 kilopascal equals 1,000 pascals. So of course you could do it this way, like you could follow the golden rule and say, okay, 1 kilopascal is 1,000 pascals, and that would end up giving you 106.370 pascals, which is fine. You can do it that way, or you can just take your decimal and move it 3 places to the right. Either one works, okay? So hopefully you got that one right. All right, let's move on. So pressure conversion should be something you should be able to do pretty quickly. All right, so section 10.3 is gas laws. So y'all know I like the gas laws. Okay, so Boyle's law states that the volume of a fixed quantity of gas maintained at constant temperature is inversely proportional to the pressure. So in other words, if you multiply pressure times volume, you're going to get a constant. So the formula is V1P1 equals V2P2. And then Charles' law, on the other hand, states that the volume of a fixed amount of gas maintained at constant pressure is directly proportional to its absolute Kelvin temperature. Okay, so you have to make sure in the gas laws, if you're using temperature, it has to be in Kelvin. So just a friendly reminder, to get there, you do degrees Celsius plus 273. Okay, that'll give you your Kelvin. So V over T gives you a constant, so the formula is V1 over T1 equals V2 over T2. Now remember though, some of y'all, you struggle if you have to solve for something in the denominator. You'll rearrange the formula wrong. So remember, we talked about in class cross multiplying. So you can cross multiply and do V1 times T2 equals V2 times T1. Okay, so you just take the top, multiply it by the bottom of the other side, and take this top and multiply it by the bottom of the other side. That way everything's in the numerator. So if that helps, do that. If you have no issue rearranging and solving for something in the denominator, then don't do that. Either one will work. But remember, you have to have temperature in Kelvin. You can't have negative because then the volume could be negative, and that's not possible. All right, so Avogadro, we talked about him before in stoichiometry. So Avogadro's hypothesis states that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So that's where we got when we were doing stoichiometry. 1 mole equals 22.4 liters at STP. That's where it came from. So 1 mole of any gas at 0 degrees Celsius and 1 ATM will contain exactly 6.02 times 10 to the 23 particles and will occupy the volume of 22.4 liters. So remember, that's when we talked about him. So 6.02 times 10 to the 23, and we also talked about that 22.4 when we were doing stoichiometry. Avogadro's law states that the volume of a gas maintained at constant temperature and pressure is directly proportional to the number of moles of the gas. So I know it's weird that moles is in, but it's number of moles. So volume over number of moles is a constant, and so his formula is V1 over N1 equals V2 over N2. So again, if you struggle with the denominator, you can cross multiply. So V1 times N2 equals V2 times N1. It still works. Alright, so like I said, it's just up to you. But yeah, if you're an AP Chem, you need to get to where you can just solve for something in the denominator. We don't need to be wasting our time with cross multiplying up in here. Alright, so let's look at this first one together. So it says, suppose we have a gas confined to a cylinder with a piston and an inlet valve. Consider the following changes. Okay, so first of all, y'all, when you see a question like this, I need you to know what this even means. Okay, so a container with a piston is, think about like a syringe. So like we have this lid, but we can kind of push it down and raise it. That's what a piston is. All right, and it says it has an inlet valve. So that means we have a little valve here, and so we can open it and put stuff in, or we can let stuff out. So it's a way to let things in and out. All right, so it says, suppose we have a combined gas. Consider the following changes. So it says, heat the gas from 298 Kelvin to 360 Kelvin while maintaining the piston's position. Okay, so y'all, if I heat this, so here, I'll put a little Bunsen burner flame under there. There we go. That's my Bunsen burner. So if we heat it, naturally the piston would want to rise. But notice it says we maintain the piston's position. So that means even though the gas particles, here, I'll just put some gas particles in here. Even though they want to spread out, if we maintain this, They can't spread out. They can move faster, but they can't spread out. So what would happen? My pressure would increase. Because you're just going to build up pressure. So my pressure increases. Alright, so that's what happens for part A. So I'm assuming there's still others since I called this part A. So I'll leave my picture up here. Alright, so it says you move the piston to reduce the volume of the gas from 1 liter to 0.5 liters. Okay, so y'all, we're taking the piston, we're going to move it down. Okay, so we're moving that thing down. So let me erase some of my particles and then put them back on here. Alright, so we moved the piston down. We still have the same amount of particles, so what's going to happen? Well, that means those particles, they're going to collide more often. Oh, we're not heating it this time. They're going to collide more often. So again, the pressure is going to increase. Okay, because as you reduce volume, pressure has to increase. That's Boyle's law. Alright, then part C says you inject additional gas through the gas inlet valve. So here what we're going to do is we're going to add some more gas. I'll just color these in. So then what would happen to pressure? Well, I mean, we're not letting that piston move. So if we add more gas, pressure is still going to increase. So these are 3 different ways we can increase pressure. We can heat it but not allow that piston to move. We can reduce the volume. That will also increase pressure. Or we can add more gas. That would also increase pressure. Alright, so like I said, if they ever talk about a piston, that's what they mean. So on the AP exam, like, draw some pictures. Sometimes a picture will help you a lot. Alright, so y'all tried this one. So it actually, what happens to the density of a gas as these 3 things happen. So pause it, try it. I will give you one helpful hint. Remember, density is mass over volume, or you can think of it how close the particles are. The closer they are, the higher the density. The more spread out they are, the lower the density. Alright, so I'll assume you tried these, and let's look at them together. So it says the gas is heated in a constant volume container. So y'all, constant volume means nothing is allowed to change. Alright, so we're going to heat it. Ooh, that's an odd looking flame. That's not Bunsen burner, y'all. You know, it looks great. Alright, so we have our particles. So if we try to heat it, they're going to start moving faster. They're going to want to expand, but of course they can't because it's constant volume. So even though they want to spread out and get less dense, there's no room to. So density actually stays the same. And y'all, those are the hardest ones, is when I give you one, or on the AP exam they give you one where it doesn't change. Because you automatically always want to put increase or decrease, but in this case it just stays the same. Whoops, oh, I'm in the wrong area. Oh, this doesn't even have any math. I don't even know why I'm looking at this. Alright, so it says the gas is compressed at constant temperature. So y'all, this would be an example of one with a piston. Okay, so we have our piston, we have our gas particles, but we compress it. So remember, that means we're just going to move our piston down. So now the particles are squeezed a little closer together. So the closer the particles are, the higher the density. So for this one, density would increase. Alright, next it says additional gas is added to a constant volume container. So we have our container, we have our gas, we add some additional gas. Well, if we add additional gas, those particles have to get closer together. So again, density would increase. Just like that. Alright, so hopefully you got that one right. So let's move on. Oh, and section 4. So we are done with part 1 of the video. Hopefully most of this stuff should have been total review from honors. So hopefully you aren't stressed out about this unit just yet.